cosmological. Thank you.
Okay, good morning. You hear me? Yeah, it's good. Okay, I try to look at the map and to see if I can give a name to each redly painted country for which you come. And I think I can, because I was a great fan of geography when I was a child, and I played a lot with all of these games that you go around the world. But I have to say that some of you come from countries that it's the first time that I teach students from these countries. It's interesting. So I was actually given a double mission, standard model and flavor physics. We will start with the standard model. It will take as much as it will take, I guess about 3 of the 6 sessions that we have. I mean, Giovanni took 5 minutes of your time. I will take 9 hours of your time, which is a lot to speak, but for you also a lot to listen. I hope you will survive to the end. To help you, there are lecture notes. They should be on the website of the school. They are long, I think some 80 pages. Almost everything that I say is in the lecture notes, so feel free just to listen and not to write down, and to be skeptical and to ask questions, and you can fill in the gaps later from the lecture notes. So I'm going to talk about the standard model. I think the standard model is a fantastic theory. It's really beautiful. But I think that to understand the beauty, you somehow have to forget the history. You don't have to describe it the way it was kind of developed, but to see the whole picture from the present perspective, which is what I'll do. Also because I'm a little bit weak on the history, but also because I think it gives a more coherent picture of the model. So almost any model that we do in particle physics should start from a definition. Oops. From a definition of the model, which I will do. I will define it. Standard model, I define it in 4 lines, 4 short lines. It's amazing to me that in 4 lines you can define a model that describes all the elementary particles known to us and all the interactions between them except gravity. From this definition, we will derive a Lagrangian, which for the standard model is again some 4 lines, but purely mathematics. From the Lagrangian, we will do 3 things. We will find the list of particles in nature. We will find the interactions among them. And we will find the symmetries that this Lagrangian has in it. Some of these will be part of the definition. These will be imposed symmetries. Some of these will not be in the definition and will be kind of a surprise. These are called accidental symmetries. We will come to that. And from that, follow phenomenology, if you want, or predictions. And experimental tests. So I will do all of this for the standard model. Perhaps here and there I will go outside of the standard model to emphasize special points of the standard model to see that it is unique in some aspects. So to give counterexamples, I'll do that from time to time. Now the definition, what do I mean by definition? Two things, the symmetries. What are the symmetries that we believe hold in nature? And spontaneous symmetry breaking. Or if you want, The symmetries are of the Lagrangian. The spontaneous symmetry breaking means that the ground state of the universe does not respect all the symmetries of the Lagrangian, but only part of them, and that will be part of my definition. And then, as you will see, our Lagrangian will contain 3 types of particles: scalars, fermions, and vector bosons. And in the definition, you have to say what are the representations of the scalars and the fermions. One of the most amazing things about modern particle physics is that I don't have to tell you what are the representations, meaning what are the transformation properties under the symmetries. So it's related. The symmetries, how do the various particles or the various fields transform under the symmetries. And the amazing thing is that you don't have to do it for the vector bosons. The symmetries will tell you which vector bosons exist in nature, what are their symmetry, what properties, what are their representations. It's quite an amazing thing that the vector bosons are imposed on us by the definition of the model. They don't have to be introduced. So we'll see that. Now, so the basic thing that we now use to define a model is symmetries. And you can think about it in 2 ways. Symmetries provide us with toolbox. We now know how to describe quite a few phenomena in nature with symmetries, or explain them. I don't know exactly what the word explain means in particle physics. I have a sense of it. So I hope to deliver that sense of what does it mean to explain. But here is the toolbox. Here are the phenomena that we know to describe or to explain starting from a symmetry principle. So there are many classes. Symmetries and their consequences. Some of their consequences. Okay. So the symmetries that we'll discuss list are space-time symmetries. And I will just mention which these are, but what they give us as a consequence is conservation, energy, momentum, and angular momentum. Okay, so invariance under translation in time give us conservation of energy. Under translation in space give us conservation of momentum. And under rotations give us angular momentum. So if you want, these features that are observed in nature are explained by symmetries. We impose the symmetry, we get these as a consequence. We have the simplest symmetries are discrete symmetries. And they give us the list of the consequences of the list that I do. What they give us is kind of selection rules. So the simplest example for a discrete symmetry is Z2. Particles can be even or odd. And the selection rule is that for the odd particles, if you want, -1 to the n, the number of odd particles under the symmetry is maintained. If you started from a single particle, you have to end up single odd particle. The process will end with 1 or 3 or 5 odd particles. And one interesting consequence, which is more general than that, the lightest particle that is odd under a Z2 symmetry is stable, because there are no lighter particles to which it can decay, and therefore it must be stable. So this is mainly selection rules. Then there are global symmetries, which are continuous. And they give us conserved charges. So for example, we'll come back to it. Baryon number is a global continuous symmetries, and the baryon charge is maintained. Then there is local continuous. Yeah. And here, perhaps the most striking consequences. Among the many consequences of that, it predicts the existence of interactions that are mediated by massless spin-1, or what we call gauge bosons. That's a really striking consequence. That's what I said, that we don't have to tell or to put in by hand vector bosons. If you impose local continuous symmetry, it predicts interactions mediated by massless gauge bosons. Then you can spontaneously break a global symmetry, global and continuous. And again, a rather strong consequence, you get massless scalars that we call Goldstone bosons. I'm telling you all of this because we will do part of it as the definition of the standard model, and I want you to understand where it will lead. And finally, there are spontaneously broken local symmetries, and this predicts interactions, again, but this time mediated by massive vector bosons. So if you observe any of these phenomena in nature, then instead of trying to describe it, we can impose the symmetry and see the consequences. And almost all of these have consequences beyond the list written here. So if you try to explain something with that, it has further consequences that you can test. So this is a rather powerful tool to understand nature. This is the stage, the last word, if you want, in particle physics, now for quite a few decades, starting from symmetry principles and ending up with experimental tests, which is the process that I will do. I will not do the experiments by myself, but I will tell you about the experiments in the standard model. I would also like to make a distinction between imposed symmetries. These are the symmetries here, the first line, the symmetries that we use as a definition of the model. This I impose on the model. And then, so this is in the definition. And one of the nice things, and actually one of the most impressive things about the standard model, is the accidental symmetries. So, and accidental symmetries are consequence of the imposed symmetries plus the particle content which is the second line, plus, and that's very important, renormalizability. Renormalizability means that we write in the Lagrangian only terms up to dimension 4 in the fields. As higher dimension terms have coefficients which have inverse powers of mass in the coefficient. And when you run into energies, or when you calculate in energies higher than that scale that appears in the denominator of the coefficient, then you run into inconsistencies. So if your model is only a low energy effective theory, then you should add also non-renormalizable terms, and these will usually break, or always will break, the accidental symmetries. So we will see that too. We'll see that in the standard model, all we impose are local, continuous, sometimes spontaneously broken. and of course space-time symmetries. So we impose these three types, and we get, for a bonus, as accidental symmetries, sorry, not spontaneously broken, but global continuous symmetries. We'll see that. What else before I go to the standard model? So these are the main consequences. Some of the additional consequences. There are forbidden couplings. Very often there are relations between couplings. One interesting thing is that the lightest particle, the lightest charged particle, and by charge, I don't mean just electromagnetically. Under any symmetry, anything that transforms under the symmetry, that is not a singlet of the symmetry, the lightest under any of the symmetries is stable. There is a symmetry, and there is a charged particle, and all the lighter particles are not charged, then you cannot conserve the charge by decaying into these neutral particles, or singlet of the symmetries. So that's an interesting thing, and it explains for us, for example, the stability of the proton. It says the stability of the electron. And additional things which also affect the standard model is that for charged fermions, again, charged under any symmetries. By charge, I mean that it transforms under the symmetry, that it's not a singlet of the symmetry. Carries charge under any of the symmetries that I impose. So charged fermions have no Majorana masses. And that's also something that we'll talk about within the standard model. And chiral fermions say in a minute what these are, have no Dirac masses. By chiral fermions, for those who do not know the terms, I mean that charge under any symmetry of left chirality fermions, there is no right-handed fermions in the theory with the same charge. Then we say that these fermions are chiral. If there is a left and a right chirality fermions that transform in the same way under the symmetry, then it's not chiral. The opposite of that is they are in a vector representation. And particles that are charged but in vector representations can have Dirac masses, or would have Dirac masses. So maybe just one more table before we really go to the standard model and define it, is a few words about Dirac fermions and Majorana fermions. Also something which is often confusing. So the number of degrees of freedom for Dirac fermions is 4. For Majorana fermions, it's 2. The representation under the symmetry for a Dirac fermion means a fermion with Dirac mass. A Majorana fermion means a fermion with Majorana mass. Okay, just clear. Here it must be in a vector representation. Here it must be neutral or singlet. Same word for me. The mass matrix. Assuming that I have M left-handed and N right-handed. Here it's M by N for Dirac fermions, and it's general. Here it's M plus N times M plus N, and it's symmetric. And within the standard model, the quarks and the charged leptons are Dirac particles. They have Dirac masses. And, well, within the standard models, we'll see neutrinos are massless, but most likely, for reasons that I will tell you, and if not I, then Sylvia in her lectures will tell you, are very likely Majorana particles, even though that has to be decided experimentally, and it's not decided yet. Actually, I think I have here a nice bet, and perhaps I bet with a physicist that neutrinos are Majorana particles. He said that they are Dirac particles, and the reason that it is a nice bet is that there are clear ways to prove that a particle is a Majorana particle, or for at least the neutrinos, to prove that they are Majorana particles. I'm not aware of any way to prove that neutrinos are Dirac particles, if they are. So I cannot lose this bet, which is always a nice bet to make, one that you cannot lose. But if you know of a way to prove that neutrinos are Dirac particles, I'll be happy to lose the bet and to become aware of this experiment that can tell us that they are Dirac particles. Okay, so all this is introduction to tell you the tools that I will use in getting the standard model. So we are at step one, definition. By the way, as far as I can tell, there is in this audience, and Giovanni will correct me if I'm wrong, a huge variety of knowledge and background, and I hope I do not lose too many of you too quickly. I don't know, I will need some feedback. So there are at least 3 people from my institute. Tell them quietly if you lost me. I mean, they're sitting here. And tell them, gossip with them, and they will tell me because they're not afraid to tell me that I lost too many of you. And then I'll see what I can do. But for the time being, I continue with my pace unless I see too many faces staring at me. And okay. So the definition of the standard model. Defining the standard model. The symmetry. Okay, we are here. Symmetry of the standard model is a local SU3, that I denote by C for color, times SU2, that I denote with a subindex L for left, times U1, that I denote with a Y for hypercharge. I don't know why it's hypercharge, but okay. That's the usual way of writing it. And the spontaneous symmetry breaking, namely the subgroup that is shared not just by the Lagrangian, but also by the ground state. Spontaneous symmetry breaking, this will be SSB from now on, is that this symmetry is broken into a subgroup, which is SU3 color cross U1 electromagnetism. And the generator of U1 electromagnetism must be a combination of generators from this group, and since SU3 color is respected, must be a combination of generators of this part of the group, and it is T3, this generator, there are T1, T2, T3, 3 generators of SU2, or if you want T plus, T minus, and T3, plus Y. That will be my definition of it. So that's the first two lines. Okay. Second is representations of scalars and fermions. Now I remember it, I can erase it. Yes? I do not impose any discrete symmetry. I said all I impose are local symmetries. Well, I impose this, and I tell you that some of them are spontaneously broken. That's it. Okay. Fermions. Fermions come in 3 copies. Each is a set of 5 different representations. We'll call them generations. Okay. So 3 copies, and I'll give them names, QL. The sub-index here stands for chirality. Okay, so this is left-handed field. And they are triplets of SU3 color. So what I have to tell you here is how they transform under this symmetry. That's the second part of the definition. So these fields, there is, okay, we put here I will run 1, 2, 3 for the 3 copies. Transform as a triplet under SU3 color, the fundamental representation of SU3. As doublets of SU2 left. Doublet is again the fundamental representation of SU2. And carry hypercharge plus 1 over 6. So that's one type. Second type, call it U right I. Again, right for right-handed chirality. It's half of 1 plus gamma 5 times psi. Also transform as triplets of SU3 color, singlets of SU2 left, and carry hypercharge plus 2/3. Third type, call it D right. Triplets of SU3 color, singlets of SU2 left, and carry hypercharge minus 1/3. Fourth type of representation, left-handed leptons, are singlets of SU3 color, doublets of SU2 left, and carry hypercharge minus 1/2. And the last, right-handed charged leptons, singlets of SU3 color, singlets of SU2 left, and carry hypercharge minus 1. And as I said, 1, 2, 3, or 3 types of these. So this is the list of fermions, and now you can see also why this is called left, because the left-handed fields transform under it, it's doublets, and the right-handed fields are all singlets of SU2 left, so it affects, or the fields that transform under it are only the left-handed fields in this definition. And the last thing that I have to tell you in my definition is the list of scalars. Here we have only one field, I call it phi. And it's a singlet of SU3 color, a doublet of SU2 left, and carry hypercharge plus 1/2. Okay, that's it. This is the standard model. Okay, in this, everything else that I say during my lecture, I think everything that I say, follows from this. That's it. Nothing that I will say does not come from that. So all the phenomenology that I'll describe you, strong interactions, weak interactions, electromagnetism, short range, universality, flavor changing neutral currents, whatever you'll hear from me starts here in this definition. So I think part of the beauty, if you can write a theory of the elementary particles and their interactions in, okay, for me, 4 lines, rather impressive theory. Okay, so we define the standard model. And now we have to write the Lagrangian of the standard model. And again, I will take 5 or 10 minutes the tour of the Lagrangians before I write down the standard model Lagrangian. So, Lagrangian, which is a function of the fields, which are functions of space-time, and of their derivatives. What do we want of Lagrangians? So, first of all, this capital phi I'll use for general fields. If I need, I will use small phi for scalar field, or specifically for the standard model field. If I need a generic name for a fermion, I will use psi. And if I use a generic name for vector boson, it will be either A mu or V mu, depending on my mood. I don't know, we'll see. So here is a list of things that I want from my Lagrangian. And most of this I just state now and will not come back to. I will come back to only very few of the requirements that I put now. So first, it's a function of the fields and their derivatives only. In particular, there is no explicit dependence on space-time coordinates, only via the fields. Okay, that guarantees translational invariance, but just mentioning it, I will not come back to this. I mean, I don't know if all of you, what's your background in quantum field theory. In what I write now, in order to understand why it is so, you need to know quantum field theory. Many of the things that I will say do not really depend on deep knowledge of quantum field theory. So so this I do for completeness now. This writing, I assume that more or less you know it. There are functions. It's a function of the fields. Taken at a single space-time point. And this means that I'm doing local field theory. So there will be no term, I don't know, phi1 at x1 and phi2 at x2. Okay? It will be phi1 at x1, phi2 at x1. All the fields are taken the same space-time point. It is real, the Lagrangian. And that guarantees, if you want, that the total probability is conserved. Intuitively, time evolution is e to the I ht, and if h is real, then e to the I ht has size 1. It's invariant under the Poincaré group. French among you will forgive me if I don't know where to put this apostrophe. I think it's here, but I'm not sure. And the Poincaré group is translations, space-time translations, and Lorentz. Okay, so I will only write such Lagrangians. I said before, this already guarantees conservation of energy, momentums, and angular momentum, but I will not. So all of these are very, very generic. Now something which is a bit tricky, analytic function of the fields. Even more explicit, it will be a polynomial in the field, the Lagrangian that I will write. And the reason is that I will discuss only, if you want, perturbative thing. I expand around the minimum, and around the minimum for the field. So the Lagrangians that I will write are expansions around that minimum, and when you expand around the minimum, it's a polynomial. So that will be my Lagrangians expanding around the minimum. At one point, I think, I will write a Lagrangian that is not analytic in the fields. It will be to save a lot of time and to get rid of would-be Goldstone bosons in an elegant way rather than in a cumbersome way, but okay. In general, this is what I'll do. I have 3 more lines and have to go to here. Requirement number 6. That's the one that is mostly the subject of these talks. It's invariant under some internal symmetries. The group. This is exactly for the standard model. It's invariant under this. This is the internal symmetry group. A symmetry that operates on the fields, not on the space-time coordinates. So, 2 more things which are not general. I will require naturalness in some very loose sense. All that I will require is that I will write down all the terms that are allowed by the symmetry. Okay, so here naturalness is not whether there is fine-tuning or whether it's, there are terms that, couplings that are quadratically divergent when you put radiative corrections. Not in this sense. Naturalness in the sense that all terms that are allowed, I will write them down. And we'll see the consequences of that. I will put no term to 0 if it's not forbidden by the symmetry. And so that's not necessarily a condition of nature, but otherwise there is not much point in building a model on the basis of symmetries. And something that I know does not hold, Renormalizability. And so again, this is writing down terms only up to dimension 4 in the fields. So no terms that have a coefficient which has inverse powers of mass in it. And this should be valid, or we should write normalizable terms if the theory that we write is only a low-energy effective theory. Now, the standard model is guaranteed to be a low-energy effective theory. Okay? It's not a theory that is valid up to infinity, up to arbitrarily high scale. There is gravity at M Planck. There is a Landau pole in the hypercharge at some 10 to the 41 GeV. There are other things. It's a low-energy effective theory. Yet, if the scale at which it stops being a good theory, the scale lambda, is much higher than the scale at which we conduct experiments, then omitting non-normalizable terms means that we are omitting terms that are suppressed by E over lambda, m to the minus 4, where there is the dimension of the term in terms of the fields. So dimension 5 are suppressed by E over lambda, dimension 6 terms by E squared over lambda squared. If the scale is high enough, then the renormalizable part of the Lagrangian is a good approximation. And okay, we'll see if things that I write at the renormalizable level fail, then I may learn about the scale at which the standard model stops being a valid theory, which is a very useful lesson from that failure. So I will write only the renormalizable part of the standard model Lagrangian as an approximation, and we'll see if it works or fails. And in one instance, it will fail, and that's the subject of a whole set of lecture on neutrinos. We'll see that there it really fails. Okay, so having said all of these things, then the Lagrangian that I can write is rather limited in the number of terms and in what can go into it. A Lagrangian in terms of scalars and fermions now, okay? So it can have 4 types of terms. So a Lagrangian of scalars and fermions can have 4 types of terms only, a renormalizable one. First, there are kinetic terms. Kinetic terms are there if we want to be able to describe the free propagation of a particle in space-time. You must write this down. If the field that you write is a dynamical thing, it represents a real particle that propagates in space-time, then these kinetic terms must be there. And we'll see that when we impose, or we will not see, but when we impose a local symmetry, then the kinetic term by themselves, as originally written, always violate a local symmetry, and we will have to correct that. So the kinetic terms will change into terms that, or will be expanded into terms that have also gauge interactions. So the gauge part of the model, as we'll see, is for me part of the kinetic terms, and we'll do that explicitly for the standard model. Second, there are terms that depend only on the fermion fields. And here things are really simple because an odd number of fermions violates Lorentz symmetry, so there must be an even number of fermions. If you write 4 fermions, it's already non-renormalizable. It is dimension 6. Each fermion field has dimension 3/2. And so the only possibility is dimension is quadratic in the fermion fields. So it's either Dirac mass term or Majorana mass term. I write it as psi, even though it's a bit more complicated, but as far as quantum numbers, it's like psi. Majorana, that's it. That's what can enter there. So mass terms for the fermions. Nothing else is in the renormalizable part of the Lagrangian and depends only on fermions. Then there is what we call a Yukawa part, which is a single scalar field and 2 fermion fields. That's dimension 4. That's the Yukawa. That's its form. And finally, there is a part that depends only on the scalar fields. And here again, so any number of scalars is still a Lorentz scalar, but if you have 5 scalar fields, it's non-renormalizable. One scalar field you can always get rid of by redefinition of the field, or if you want, when we expand around the minimum, which is what I said, as I said, this is what I do when I write my Lagrangian, then there are no linear terms. And so here there are 3 possibilities: phi squared, phi cubed, and phi to the 4th terms. That's it. This is all that I can write. The form of the kinetic terms is entirely dictated. I mean, it's only a question of normalization, and there is something called canonical normalization, where each kinetic term has a known number as its coefficient. And in that canonical normalization is the normalization where we know how to interpret all the other terms. We understand that the term which is quadratic, say in the fields, is a mass, ms squared, and we understand everything, so we will always use the canonical normalization. So that's totally dictated once we know what the degrees of freedom are. And then there are these three parts, purely fermionic, purely scalar, and Yukawa terms, which involve both. And we have to see what is allowed under each of these. And when I write the standard model Lagrangian, which is something that I will now do, it's a specific form of renormalizable. Yes? Sorry?
Yeah. So the L phi psi, whatever you have written in the first line, has to conserve the SU2L cross the...
I did not yet write the standard model Lagrangian. This is now the most general renormalizable Lagrangian.
Okay.
I will now say what...
So actually, I was just thinking that how can you construct a singlet out of 3 SU2L doublets? The phi cube term that you've written there after the L phi will not be allowed.
I will soon do it, so you'll see. It will not be 3 doublets. It will be 2 doublets and a singlet.
Yeah. That's,
but I will soon come
it was
to
the
it.
general case that you were writing.
I'm not yet in the standard model, okay?
Okay.
This is...
Then why are you avoiding the single phi term? So what is the charges of the phi that you have written in the first line? What are the it is just a general scalar, right?
This is generic scalar and generic fermions. I'm just saying this is the most general form of the Lagrangian. This phi cubed, for example, could be phi 1, phi 2, phi 3, 3 different fields, or phi 1 cubed, or whatever. So this is just representing the general form of terms that can appear, that are polynomials in the field, that are normalizable, and they are
so they can be also singlets under all symmetries, this phi?
Yes.
Then why are you avoiding the phi simple for the L of phi? Phi to the 1?
Phi to the 1 I said we can get rid of by redefinition of the field.
Okay.
Or, if you want, when we expand around the minimum, there is no term which is just phi.
Okay.
Because that would means that this is not the minimum.
Okay.
The vacuum expectation value is not 0, and so you have to shift the minimum to elsewhere, and then you get rid of the single phi term.
Okay. Thank you, sir.
So this is L, generic. Just saying this is the most general thing that can have, which is renormalizable. And standard model will be a specific form of renormalizable L of Q, U, D, L, E, and phi, the fields that appear there, each with 3 copies, which is subject to the local symmetry and which leads to the spontaneous symmetry breaking into SU3 color cross U1 electromagnetism. So I'll have to go for each of these categories and see for these fields with these transformation properties which terms are allowed, and I will write down all the allowed terms and which are forbidden. So this is what we are going to do now. Write down the standard model, and at this point, what's important is analytic, renormalizable, and invariant under the internal symmetries. All of these I take for granted. They're already in the most general form that I wrote there. All of them. Okay. So, yes. They will be forced on me by imposing the local symmetry. So I'm saying, I mentioned them, I said that the kinetic term by themselves would violate if there are fields that are charged under the local symmetries. Then for these fields, the kinetic terms, as originally written, would violate the local symmetry. in order to save it, I will have to introduce spin 1 fields with well-defined transformation properties under the symmetry. So all this will be a prediction, if you want, of the model rather than an input. But yes, L-kinetic includes in it gauge terms. This, yes?
Why do you choose the irreducible representation? You can choose other one.
So here, the question of why stops. I mean, this is the definition of the model. Okay, given this model, I know how to explain a huge amount of phenomena in nature. Why using this model?
Okay, but in principle,
I know it works.
In principle, you can choose another one and fit the...
Yes, okay. Yes. Actually, maybe if time allows, and if the lecturer on neutrinos is not angry at me at some point, I will do an exercise of the same model, just adding 3 of these, which so far we don't have, and we'll see what will be the consequence of that. So I think it will connect nicely actually with the lectures on neutrinos. So I will do this, and I will also do, at some point, a very little exercise of writing here, instead of 3, 2. And believe it or not, I will even do an exercise of writing there 1.5 instead of 3, but we'll see what I mean by that. So I will do a bit of variations on that and see consequences. Of course, this was created historically because we observed certain phenomena and we built the model to explain these phenomena. But I'm an arrogant theorist. I'm saying, let's start with a theory. Let's say this is nature. Let's see what's the consequences, okay?
Okay.
And we'll find a fantastic agreement with nature, okay? So it's an experimentalist would give you these lectures, it would be a completely different spirit and theme and order of logic, okay? So I'm taking the liberty of me being the speaker and describing it, but that's nature. I'm guessing, okay? Yes?
The requirements for so you have just erased the 5th requirement is the analyticity of the functions. So I'm wondering whether the renormalizability is already included analytic requirements.
Well, if you write terms that are not analytic, then you can start to expand them perhaps in some way as a polynomial, and then you'll have to stop at some point because of renormalizability. But I will not do it, okay? But yeah, it's if you say have a term that is exponential in the field, then it's also non-renormalizable. I mean, some parts of it are non-renormalizable.
But if we require the renormalizability, do we already force it to be a polynomial, which will be analytic functions already?
It's a good question. Let me think about it before answering a hasty answer, okay? Yeah. Okay, so we are now here, finding the standard model Lagrangian, going one term after the other, and seeing what's allowed and what's not allowed, what appears and what's not there. So, yeah, maybe if I would just write the kinetic terms and forget about the symmetries of these fields, then my Lagrangian, the kinetic part of my Lagrangian would look like this. I think minus, yeah, d mu phi dagger, d mu phi for the scalar, and minus I q left I bar d slash q left I, minus I u right I bar d slash u right I, minus I d right I bar d slash d right I, minus I a left bar d slash a left I, minus I e right I bar d slash e right I. And writing twice I means I sum over this. So these would be the kinetic terms, and I want them there because I want to describe the free propagation of the particles that are related to these fields. However, there is a problem here that this violates the local symmetry, all the local symmetry. All the other terms, by the way, do not violate. Okay, if I write terms that respect, so this respect, if this were a global symmetry, where it will just require global SU3 cross SU2 cross U1, then these terms are all singlets of the global symmetry. But the local symmetry, it violates, and let me just give a feeling for that. I hope that roughly, yes? That bar is Q dagger gamma 0. Oh, these are, at the moment, wild fields, actually. But, yeah, they will become Dirac or Majorana when we write the terms in terms of mass eigenstates. These are not mass eigenstates. These are fields with well-defined transformation properties. So these are two components wild fields that I write at the moment. But, again, yeah. Okay, so some generic field phi under some symmetry. Let's make it easy. Let's take a U1. It goes to e to the I q theta of x phi, if it has charge q. And the special thing about local, unlike local, is that this theta here, parameter, is a function of space-time. And so d mu phi goes under the symmetry into d mu of e to the I q theta of x, right? And this has two parts, e to the I q theta of x and d mu phi, and plus I q e to the I q theta of x and d mu theta of x phi. And this second term is the problem, because if the symmetry is global, then theta is a constant of space-time. D mu of theta would vanish. We would have only the first time. And then, say, in d mu phi dagger, d mu phi, this IQ would cancel, and the term will remain invariant. So the first term is okay. The second term is a problem, and if you put this, say, into here, you will see that it violates the symmetry. This term has, and under the transformation, there are additional things beyond d mu phi dagger, d mu phi. So that's the violation. And then the idea of saving local symmetry, but maintaining these terms. So these terms, I want them in the Lagrangian. They must appear there. So saving the symmetry and having these terms, the only solution that is possible is to replace everywhere d mu, del mu, this partial derivative, with something that we call the covariant derivative, that is d mu plus I d, an arbitrary dimensionless parameter, q, the charge of the field on which it operates, a mu, a vector field. I have to introduce this vector field. It's the only way to save this, okay? I have two requirements. I need this term in the Lagrangian, and I want local symmetry. Then to do it, I must introduce a new vector field with a well-defined transformation property under the symmetry. A mu under the symmetry goes to a mu minus 1 over g d mu theta. And then you can check it. D mu phi does transform into just e to the I q theta of x d mu phi. And therefore, d mu phi dagger, d mu phi transform to itself. It's invariant. So this is how we, the way in which a local symmetry forces us to introduce vector fields. They have well-defined transformation properties. We know what they are. For a non-abelian group, they must be in the joint representation of the gauge group. Again, I will not explain all of this here. And you must introduce them. Now, once we introduce them, then by what I termed naturalness, we want to write the terms that are allowed. In particular, we want to think that these are dynamical fields and have kinetic terms by themselves. And to write a kinetic term for a vector field, the right way to do it is to define F mu nu as d mu a nu minus d nu a mu. And then minus quarter F mu nu is a kinetic term for the vector field, which is fine. But you cannot write a term like half m squared a mu, a mass term, because under this transformation that is forced on us in order to solve the local invariance of the kinetic terms for the scalars and fermions, such a term would violate the symmetry. So we are forced to introduce vector fields. They must be in the joint representation of a non-abelian gauge group or neutral under an abelian group, and they are massless. We cannot write a quadratic term in these fields because it would violate the local symmetry. So all of that is by having dynamical fields that transform scalars or fermions that transform under a local symmetry. All this extra structure is imposed on us. So this is a very powerful thing, this starting point. You impose the symmetry, you get extra fields. Okay, so let's do it for the standard model. Right, we impose SU3 cross SU2 cross U1. Local. This symmetry forces us to introduce 12 degrees of freedom of vector bosons. Let me give them names. There must be a vector field in the adjoint representation of SU3 and a singlet of SU2 and with no hypercharge. And there must be, so this is 8 degrees of freedom, a field WA, which is a singlet of SU3 color and a triplet, the adjoint of SU2, no hypercharge. And there must be a field for the local U1 hypercharge, which is a singlet of all the symmetry. So the existence of these fields is a consequence of imposing this local symmetry. And to write kinetic terms from these, I have to define the appropriate, what we call field strengths, these things, which for fields that are in the adjoint of a non-abelian group is a bit less trivial. It's d mu g nu a minus d nu g mu a minus g strong. It's this arbitrary dimensionless here, but now it's independent for each of these. So for the SU3, I call it GS, G strong, F, A, B, C, G, mu, A, G, nu, sorry, G, mu, B, G, nu, C. And the FABC is something that we call structure constants. They come with the group. I mean, these are known numbers. And essentially, they are in the commutation relation. So if TA, TB, the commutator is, and maybe there is an I here, FABC, TC. So these are known numbers for each group. And here it's the structure constant of SU3. And there is a W mu nu A, which is d mu W nu A minus d nu W mu A minus another dimensionless parameter, G, and epsilon ABC, which are the structure constant of SU2. Epsilon 1 to 3 is 1. Any odd permutation of that changes the sign. And if you have two indices which are the same, it's 0. So it's an antisymmetric. And W mu B, W mu C. And B mu nu, simplest because it's an abelian group. So it is just this. And okay. So I introduced the field to have the local symmetry. I defined the field strengths. And the important part is that for each scalar of fermion, there is a covariant derivative which is specific to that field. It's specific because each of these has different transformation properties under the group, and these transformation properties define what this covariant derivative is. So it always has this d mu in it, because we want the kinetic terms to remain as they are. And then there is I, G, S, G, mu, A, LA. And LA is here the generator of SU3 in the representation that is specific to the field. Now, all our fields are either triplets or singlets of SU3 color. So there are only two possibilities. If it's a triplet, then what appears here is half of lambda A, where lambda A is a set of 8 matrices, which are called Gell-Mann matrices, and they have a known form. Okay? You can find the list of these 8 matrices. These are 3 by 3 matrices. Okay? And if it's a singlet, the field, then LA is 0. And all our fields are either triplets or singlets, so I gave it all to you, all that you need. And then there is I, G, W, mu, A, and W, B, TB. And TB is the generator of SU2 in the representation of specific to the field. Now, all the SU2 representations that we have are either singlets or doublets. So all I have to tell you is the form of TB for doublets and singlets. For doublets, it's half of tau B, where tau B are the 2 by 2 Pauli matrices. Okay, tau 1, tau 2, tau 3, or sometimes tau X, tau Y, tau Z, 3 known matrices. Right? Tau 3 is 1 minus 1 on the diagonal, and Y is tau X is 1 and 1 on the off diagonal, and I and minus I for the third one. And for singlets, 0. And finally, plus I, B prime. That's the third parameter, the one that corresponds to the U1 hypercharge. And Y, simply the charge under U1Y, and B mu. And Y is this sub-index here for each field, either -1 or -half or -1/3, etc., depending on the field. Good. So now everything that you need in order to write the kinetic term is on the board. And everything is dictated by the definition of the model. What I have to do is replace everywhere this del slash with this. So d mu phi, this slash, this slash, this slash, this slash, this slash. I do not particularly like this notation because D is different depending on the field on which it acts. And usually it's written with the same letter D everywhere. But it's a different D here and here and here. You have to remember it, that it depends on the field. So, I don't know, let's take 2 examples. You can do the rest by yourself. Yes?
Why do we merely interested in a joint representation and fundamental representation of these like fields?
For the fields that we introduced here?
Yeah, for SU3 and SU2, why we are like interested
essentially, because under an SU3 transformation, for example, the transformation of some field is e to the I theta A, call it, I don't know, LA phi. And so there are here really, if you want, so LA are in the joint, right? This is the generators. The generators themselves are in the joint representation of the group. So for each generator, you have an independent transformation here, okay? You have a different parameter, if you want, that is, right? You have here 8 transformations, and you have to compensate for these 8. For each generator, you have to compensate for the local transformation by that generator. And since the generators are in the joint representation, then the compensation of that must come from fields that are also in the joint representation of the group. So that's why the vector fields that we introduce have to be in the joint representation of the corresponding group.
Okay, I understand why we're using for compensating the algebra, but why just these 2 representations? I mean, fundamental is okay, a joint representation is okay for compensating the algebra, but why not other representations? I mean, are they, I think there are other EREPs for the group representation?
The fact that here there are only fundamental representations or singlets is an interesting fact. I mean, that's what nature, again, here I postulate the model, but nature, so far, the elementary particles that we observe come only from fundamentals or singlets. And why that is so is a deep question. And maybe it's a hint of something. Here, we don't, I mean, you could introduce additional fields. We don't see corresponding particles in nature at the moment. But maybe there are. And maybe the fact that there are here only fundamentals or singlets is a hint of something, some deeper principle. This principle is not part of the standard model. Here it's just a list of representations, happens to fit nature and happens to have nothing beyond fundamentals. The fact that the vector bosons are in a joint representation is a prediction of the local symmetry. Okay, so that's something that we understand. Why the vector bosons are in a joint representation is something that we explain, if you want, or we understand from the local symmetry. Why the scalars and the fermions are only in the fundamental, we don't know.
Okay, so nothing outlaws any other EREPs of this?
No, and actually, saying grand unified theories, you usually have to include, so for example, if you have an SU5 symmetry that is broken to this SU3 cross SU2 cross U1, you have to introduce also scalars in the adjoint representation of SU5, not just in the fundamental, to break the symmetry appropriately. So it's not some principle of nature, it seems. But the low energy phenomenon, the physics or the phenomenology related to the standard model requires only these representations. Okay, so let's do 2 examples. D mu QL. This field. So first of all, there is d mu. That's always the case. Second, we see that it's a triplet of SU3. So there is I GS I over 2 GS G mu A lambda A. Lambda A, 3 by 3 Gell-Mann matrix, a known matrix. It's a doublet of SU2, so there is I over 2 G W mu B tau B. Tau B is the 2 by 2 matrix, the Pauli matrix, a known one. And its hypercharge is 1,6, so there is I over 6 G prime B mu. All of this acting on UL. Okay, so that's it. But you see that the covariant derivative is definitely depending on which field it enters. Don't let the use of the same. So let's do one more example to see on the scalar field, d mu phi. It's d mu. Phi is a singlet of SU3 color, so it's 0, and the term with the gluon field, the octet of SU3, does not appear. It's again a doublet of SU2, so there is an I over 2 G W mu B tau B, and it has hypercharge of plus 1/2, so plus I over 2 G prime B mu. All that acting on phi. And you can do it for all the other fields. So, by imposing the local symmetry, we were led to introduce vector fields in the adjoint representation. We know that they are massless. You cannot write mass squared term for them. And all the part that is now in the what I called L-kinetic, which is much more complicated than originally because it has these D's instead of the del, and the D is sometimes quite complicated. But all of that, up to values of 3 parameters, GS, G, and G prime, is completely dictated. Only the numerical values of these 3 parameters is unknown. So there are here a huge amount of terms here. If you put all of this into that, it all depends on just 3 parameters, so it's extremely predictive, as we will see. In principle, you have to do 3 appropriate measurements, and you know everything about these terms, which include in them the interactions, the gauge interactions, okay? So all the gauge interactions are coming from here. We'll see it complicates a little in the mass basis. And everything here is known up to 3 numbers that have to be determined by experiment. Now, in addition, so this is not the end because we have now additional kinetic term related to the vector boson that we had to introduce. So there is a minus a quarter of G mu nu A G A mu nu minus a quarter of W mu nu B W B nu minus a quarter of B mu nu B mu nu. We are done with the kinetic part. On one hand side, it has a lot of terms. On the other hand side, it's all up to 3 numbers dictated by the definition. There is no freedom here to play. It's the local symmetry, which is an extremely powerful input into the model. Let me just say, I'll stop in a minute. So, it's a 3-point, L-kinetic, completely determined by the definition of the standard model up to the values of G, S, G, and G prime. And 2 more points which will become clearer, but let me say the terms, this part is flavor universal and CP conserving. Let me just say, so here there is a sum over I. So I could write it as, if you want, all I, 1, 2, 3 have the same D because they have the same quantum numbers. So I could write it, if you want, as Q left 1 bar, Q left 2 bar, Q left 3 bar, and Q left 1, Q left 2, Q left 3. And what I'm saying is that this slash is times a unit matrix. Okay, there are no off-diagonal terms, and the coefficient is the same. This is the canonical normalization. Okay, so in free propagation in space-time, these fields at the moment are, remains its own. So the fact that it's unit matrix is what I mean by flavor universal. Okay, we'll come back to it and become more precise about this. And the fact that it's CP conserving has to do with the fact that S, G, and G prime have to be real. That's the requirement of the Lagrangian is real. These terms are self-Hermitian, and so these coefficients are real. And we'll come back to these points later. I just want to mention it now. Yeah, so we are done with L-kinetic, which is the most complicated part, and we'll continue to psi, Yukawa, and phi after lunch, I guess. So I'll stop here.